Krista has given us an overview of some of the measurement techniques that have been used in the past that we want to use in the future. But now we're going to shift even further into reality, because while there's a lot that we need to do on the ground, we recognize that we need a spacecraft mission to measure things like the magnetic field, the gravity field, to look for density waves in the rings. So we need a space mission to do that, but a spacecraft can't do everything. There are a lot of constraints and limitations on it, and that's what we'll be hearing about now. Our next speaker is Marzia Parisi. She's a research scientist at the Jet Propulsion Lab. I work there, you think I could say that? She's in the Planetary Radar and Radio Science group, and that is her area of expertise, is using radio science techniques to study planets, both by tracking the Doppler shift of the spacecraft's carrier signal to look at the gravity field, and passing the radio signal of the spacecraft through the atmosphere, and from how the signal is perturbed, learning about the atmosphere. She has worked on NASA's Cassini mission and currently is associated with the Juno mission and ESA's JUICE and Bepi Colombo spacecraft. And so she is going to now tell us about the practical realities and constraints on doing a space mission. Thank you, Marzia.
All right, so thank you for the speakers that came before me, because they gave a great introduction to the Uranus environment. So now we're going to go into the nitty-gritty of mission design, because ultimately we want to design a mission that is going to answer some, if not all, of the questions that have been pointed out. But at the same time, we also want the mission to be feasible, credible, and also to align to the vision that NASA, or the programmatic reality of the mission itself. So some of the topics that I would say most of the topics I'm going to talk about actually apply to any space missions, but then we're going to see also like a few details or a few characteristics that are just special to Uranus. All right, so this is the outline. I'm going to start with talking about Voyager 2, although thank you, Krista, for talking about all the measurements and the payload. So I'm going to point out more the constraints on that mission that we will see actually will influence the constraints on our future flagship mission to Uranus. We're going to then introduce what is the life cycle of a space mission and some principle of mission design. We're going to talk about payload and trajectory. And then because my background is gravity science, I'm going to show you how these constraints actually apply to real-life experiments that fly on a space mission. And then we're going to talk about risk mitigation strategies specific to the Uranus environment. And we're going to talk briefly also about probe science and how we plan to release the probe into Uranus. And we're going to finish with current recommendations and takeaway message. So this, I don't know if it was introduced before, but this acronym that you're going to see a lot, it stands for Uranus Orbiter and Probe. So for brevity, I'm just going to call it UOP. All right. So I'm going to skip actually on some of the details. I'm just going to say that sometimes when people think about not only Voyager 2, but space missions in general, maybe not the people in this room, but in general, the public, they think that missions are very neatly designed and things just happen in a sequential order. But the reality is that we know that it's much more complicated than that. So for Voyager 2 and actually also Voyager 1, scientists realized early that at the end of the 70s and then into the 80s as well, there was going to be this alignment, this once-in-a-lifetime alignment of the four giant planets. And so this is for an example of a astronomical constraint that influenced what NASA was going to do. And so Voyager 2 did, in fact, perform flybys of all the four giant planets. And I think people think about Voyager 2, think about the longevity. So I just put here a quote from one of Ed Stone's papers, that if there are no catastrophic failures, Voyager 1 and 2 should continue to relay data well into the next century, and also at distances beyond 100 astronomical units. All right, so I think Krista actually talked about most of the geometry for the flyby. So I'm just going to point out that there were many mission constraints. For example, one of those was that the Deep Space Network was, oops, sorry, what did I do? Okay. So because of the southern declinations of Uranus during that season, then the DSN had a problem into basically organizing its visibility from the Earth. And therefore, because NASA only has one station in the southern hemisphere, which is Canberra, excuse me, then basically it had to really well define when we were gonna do the flybys of Uranus and when we were gonna relay the data back. Okay, so this is just to remind people what is the life cycle of a NASA mission. Currently, oops, sorry, I'll continue doing that. Currently, we are in pre-phase A of our UOP, and this is the phase where concept studies are done and when general ideas for several mission architectures are just put out there. And this architecture have to address the science questions that we talked about, the other speakers have talked about. After pre-phase A, we go into phase A, which develops they narrow down into one mission and system architecture that is credible and responsive to the programmatic expectations. And this comes after the mission is actually approved for formulation. And this actually comes in many forms. It's not just NASA or another space agency saying, okay, now you're approved for formulation. It can be competed. It can be actually just NASA telling you that. But let's just say that this is when the actual real work starts, and we go into then phase B, where we have preliminary design, where there is engineering prototyping, and we also assess what is the heritage for other instruments and so on. And then after phase B, the mission is approved for implementation, and this is when the team completes the preliminary design and the technology development. Then after the approval for implementation, we go into phase C, which is the actual final design and fabrication. Phase D is when the spacecraft is actually integrated, assembled, and launched. And then phase E, also known as operation phase, is when we actually conduct the prime mission. We collect all the data, we use the data to answer our science questions, and we communicate with the spacecraft, we monitor the health, and so on. And then phase F is decommission and disposal. Okay, so mission design is the fine art of balancing resources that are very limited in space. For example, this is not an exhaustive list. You have cost, mass, power, data volume, delta V, type of orbits, and number of orbits. And so obviously it's an iterative process. It's not doesn't just take one take. And there are some ground rules or constraints that come from, let's say, outside of the team, which is the cost cap, for example, what launch vehicle and what is your launch window that you're going to use. And then also international participation. We will talk about it later. It's very important. And so we start from the science. The science informs the payload. Krista talked about possible payload for a UOP. We're going to talk about it more in a few slides. But of course, to answer your science question, you need instruments. And then some of the instruments will require some types of orbit. Other instruments will require other orbits. So of course, from the payload, this informs the orbits, which in turn informs all of the other subsystems, attitude and orbit control system, power, the launch vehicle, communications. And then once the design of all of the subsystems is done, then you end up with a system configuration which can or cannot meet your requirements, and so you start over by iterating again to the payload. Now, when I was making this slide, I thought, does this arrow ever go to the science? Well, in theory, no, but it could happen, I think, from experience. Okay. So now, how is the payload of the mission actually chosen? So one way to think about it is, so we have these limited resources of mass and power and delta V. And so the system engineers could say, OK, each instrument has this much delta V, this much power, and then it's a very, make it work, basically, with the instruments that you need to answer your questions. The other way to think about it is, citing the Cassini resource exchange experiment, which basically was each instrument started with some allocation of power, mass, and so on, but then they were actually allowed to exchange between teams. And okay, now it wasn't me this time, I promise. Okay. And so basically, this is more of a market-based economy kind of thing. And the funny thing is that at the end of this experiment, it turned out that how much mass and cost increased was actually less than expected. So it was a success. All right, so now we don't have the time to go into the details of the payloads of all of these great missions here, but just to remind, in general, there are 3 categories of NASA missions. The Discovery is the smaller scale, and for all general purposes, I will say it's capped at $500 million. And New Frontiers is the middle-sized missions, and it's capped at $1 billion. And then we have the large strategic science missions, which basically they're not competed. It's NASA saying to one of its centers, OK, just make this mission for me. And so there is a general behavior that the payload will increase from the smaller scale to the middle scale and to the flagships. But it's not always like that. For example, if you look at the missions that are going to Jupiter, they tend to have a pretty large payload because it includes also the radiation vault that is basically protecting the electronics. And so for the UOP, if we're gonna compare to previous NASA missions, then you will think that it's going to compare more to Cassini and to Europa Clipper, but the reality is that it's also going farther away. And so somewhere between 6 to 9 instruments and a mass of 70 to 150 kilograms is more what the current thinking is for a UOP mission. OK, so this is a slide that I found on one of the NASA studies. It basically shows the increase in mass and cost between phase B and phase, basically after launch, so phase D, let's say. And so it's for the payload and the spacecraft, the bus itself. So for the bus itself, there is an increase of 33% in mass and 44% in cost. So it's going to weigh 33% more and cost 44% more than what you thought at the beginning. For the payload, this is 60% heavier and 100% more costly. And so the reason is that the payload resources are much more uncertain than the bus. I mean, the bus can rely on a lot of heritage. I'm not saying that there's no technological development. Of course there is, but for the payload, sometimes this is inevitable to have some technology development, and then usually increases cost and risk for the mission. And so, OK, so this is just a slide. I don't know how many of you are familiar with Aikin's laws of spacecraft design. So it's a collection of anecdotal laws. Some of them are pretty famous, like better is the enemy of good. which means that eventually when you're designing a spacecraft, you will have to come to the understanding that you have to. This is as good as it gets, right? You cannot have a perfect spacecraft with all the instruments that you want. Another one of my favorites is number 29, which is to get an accurate estimate of final program requirements, multiply the initial time estimates by pi, and slide the decimal point on the cost estimates one place to the right, which is, ouch. Okay, so I highly recommend you go and look at them. Some of them are hilarious. Okay, now coming into more of the details of our Uranus mission. So all of the resources that we talked about, mass, cost, volume, they're all limited, but at Uranus, especially power is a very limited resource because we're very far from Earth and the sun. And so the power that you need, it's not only to power your payload and the spacecraft subsystems, but it's also to communicate back to Earth because, I think when people think about Uranus, okay, yeah, it's far, but it's really, really far, even compared to Jupiter, for example. And you are downlinking your data, and the strength of the signal is decaying as with a square law. And so by the time that it gets to Earth, the signal is pretty faint. And this is an issue that also a mission like New Horizons had when they had to downlink the data. And so current estimates estimate that we will need a power between 350 and 450 watts. And there are many ways to, well, many, not really many, really two ways to power a spacecraft, which is, we could use radioisotope thermoelectric generators, the next generation, also known as NGRTG. And this is what actually was assumed in the Uranus Orbiter and Probe Decadal Survey study. And this, obviously this comes also with caveats. For example, this will not be ready until 2029, possibly. And it also depends on the availability of plutonium and so on. The other way that people power a spacecraft is solar power. For example, Juno, but also Europa Clipper will be JUICE. And so it is possible to use solar power even at great distances. But at Uranus, it's very challenging, so much so that actually in some of the studies, we thought that maybe we will do solar power staging, where we will use solar power at the beginning, like when we're flying by the inner planets, and then the staging is shed, and we're going to use RTGs for the rest of the missions. Another very limited resource is data rate and data volume as a consequence. And how much data rate you have available at data volume depends on the power of the spacecraft, but also the frequency and bandwidth of the radio carrier that you're using. And then I just wanted to point out that instruments can be at the very far end of data volume requirements, while all instruments require mass and volume and power. Some instruments like gravity science, for example, we don't really need data volume allocation because we look at the radio carrier itself and not at the modulation of the radio carrier. So now we're going to talk about a possible payload for UOP. And because this workshop is centered at the, on the interior structure of Uranus, we're going to talk about 4 instruments that do just that. And this is just an example, by the way. This is not the only answer. It's not the only payload possible for a Uranus mission, even if it's focused on the interior science. So we have a gravity instrument, example from the Juno KAT, a magnetometer, example from Cassini, a microwave sounder, example from Juno, and a Doppler imager, which doesn't have an image because actually this instrument doesn't exist yet. And you see all of them have pretty different requirements when it comes to mass and power, some more than others. For example, the microwave sounder and the Doppler imager, as it is now, I don't know how it will be in 20 years from now, they are heavier, for example, than gravity science and the magnetometer itself. And they also, I know for sure the Doppler imager, they do require a lot of data volume because they do take full disk images, and we do have to download all of that data down to the Earth. So let's see, if we add up all the mass and the number of instruments, we end up with 4 instruments out of maybe 6 and 9, and then about 80 kilograms for a total payload mass of 70 to 150. So is it feasible that all of these instruments will fly on a Uranus mission? Maybe, but we have to consider that there are also people that want to observe the moons. And yes, these instruments are useful at the moons as well, but there are your cameras and spectrometers, and there's the plasma suite. Plasma people want to make those measurements. And so most likely than not, we will have to compromise on what we can fly for interior science. Okay. So one thing that must be leveraged for mission success is the international participation. So this is one way to reduce payload costs and maximize the scientific return of the mission, because basically this doesn't count towards the NASA cap of the cost of the mission. And so, for example, taking the example of New Frontiers of Juno, because I work on Juno, the X million dollars that the KAT is worth doesn't count towards the cap of the $1 billion. And so this is one way to reduce costs. However, you still have to, the instrument still goes on the spacecraft, so you still have to budget for power and volume occupancy and mass. And so yes, you do save the money of the instrument itself, but you still have to host it on the spacecraft. And then another thing that I wanted to point out, this is from a paper by Heidi Hamel. She says that it's highly advantageous for mission teams to start engaging early with industry partners and also international partnership as well. And so I hope this is what we will be doing this week at the workshop by strengthening these connections between international teams. And by the way, these are just 2 examples of international participation, but I really could have numerous on this slide. So we talked about Juno, and this one is the Huygens probe that was attached to the Cassini mission and went into Titan's atmosphere. Okay, now we talked about payload, and now we're gonna talk about trajectory. So the reason why I talked about Voyager 2 at the beginning is that the Uranus season is actually putting some constraints on our mission design. And the reason is that during the flyby of Voyager 2, Uranus was at its southern summer solstice, which means that the southern hemisphere was basically looking at us, and it was illuminated by the sun. And so by proxy, also the moons were illuminated only in the southern hemisphere. And so this is 1986. Then we went to northern spring equinox in 2007. Now we are somewhere here, right? It's 2023. In 2028, we will be at the northern summer solstice. And so it means that the North Pole is illuminated completely by the sun. And then, again, because each Uranus season is 21 Earth years, then we, towards 2050, we will be in equinox again. And so, it's basically both hemispheres are illuminated. But then if we go beyond 2050, we will start going again towards the same configuration that was during Voyager 2. So ideally, we want to avoid that because we want to observe Uranus in different relative positions. And so if we are here now, well, we're not going to get there for the northern solstice, right, summer solstice, but the idea is to get here in the late 40s, early 50s, well, I should say late 40s, so that we can actually image the satellites in their northern hemispheres.
10 minutes.
Okay. So, so once we are there, so we talked about cruise, what we're going to do. So remember that there are different requirements for orbits. If we want to do, for example, gravity or gravity science or magnetometer, you want to get magnetic field measurements, because we want to ideally go within the rings and the atmosphere, and then we want to be in a polar trajectory because we want to sample those latitudes. We don't want to sample the same latitude all the time. But then moon science or satellite science, they want to be in equatorial orbit because they want to do flybys of the moons. And so this is an example for Cassini. Each color is a different, there is, I believe green is prime mission, and then all the other colors are the subsequent extended missions. But this is just to show you how complicated it can get, but beautiful also, really. And it's called the ball of yarn for a reason. And so we do hope that we will be able to do something similar with UOP. However, just as a reminder, we do have to get those mission requirements, these measurement requirements during the prime mission. We need to make the measurements during the prime mission. And so the other, let's say, resource that we can talk about is delta V. So delta V is the ability to change the spacecraft's velocity in magnitude and direction. And so for outer solar system missions, a representative target is 3 kilometers per second. And so we have, this is our budget for delta V. So we have to consider at least 1.6 kilometers per second for Uranus orbit insertion. Then we have 0.5 for the tour phase, so the moons. Oops, this is a typo. And then disposal of the spacecraft, 0.2 for the probe phase, 0.4 for deep space maneuvers, and 0.3 are left for gravity science and magnetosphere. Magnetic field science. And so, for example, we could say, okay, can't you do like Cassini, that you're going to use a satellite to change your inclination? Well, the issue is that we don't have a Titan at Uranus. And so it is possible to use the outer satellites to transition between equatorial and moderately being the important word, inclined orbits. But this can take some time. And so there is a balance. Do you prefer to spend delta V but get your measurements fast, or do you want to save delta V and wait? But also waiting comes with its own costs, right? You have to fund a team that is operating your spacecraft and so on. So it doesn't come for free. And so even for gravity, or what we can call gravity, let's call them gravity orbits, right? Which are, okay, let's get very close to the planet so that we can get the gravity field. There is the idea that there are two types of orbits. There are two ways of doing that. You can always be outside of the rings, and basically your pericenters are limited at very high latitudes, or you can go inside the rings and between the rings and the atmosphere. But this comes with its own issues, right? Here, it is demonstrated that you get a better gravity field. And I'm not sure about the magnetic field. It's not my expertise, but I'm going to go out on a limb and say that this is better for magnetic field measurements as well. And so, but even in the case where you get exactly what you want, then you have to consider, for example, visibility from the Earth, like we talked for Voyager 2 about the DSN, being very difficult to schedule in the sense that you have to make all the pieces of the puzzle work together. But then also, for example, okay, if during pericenter, which instrument gets to do their observations? And then I could say gravity gets to do it, right? But then people can come back to me and say, no, but it's important that we do, for example, let's say the camera might have a different point mean requirements and so on. So it's not a given, that you're gonna get exactly what you want all the time. So you could say, okay, let's do more orbits, right? Instead of doing, 6, let's do 60. But again, it's a matter of, do we have the delta V to do that? And even if we do have the delta V, do we have the time, right? Because can you wait years? Maybe, or maybe not. It depends on a lot of balancing that you have to do. And so speaking about the ring hazard, I'm going to touch on this quickly. So it is actually really hard to predict what the ring environment is going to be at Uranus. We don't know much about the particle population there. And so the Cassini mission has taught us that actually, they found a much less harsh environment at Saturn than they expected. But then, so you could say, okay, just get very close to the planet and just avoid the rings. But then you have the issue of the atmospheric torque that can potentially you could potentially lose control of the spacecraft. And so some studies suggest that there is significant cooling of the atmosphere, and which means yes, higher densities, but it means also that the atmosphere can be lower than you expect. And then in that case, you don't have the atmospheric drag that it's helping you cleaning out all of these ring particles, and so you could end up with a much more populated region that you expected. And so one answer is, okay, we might keep these orbits for the end of the mission. That is, it's less risky, but that has consequences, for example, for a possible extended mission, because I would rather say most missions do want to be extended, and so if you are doing the risky part at the end, that might jeopardize your ability to do an extended mission. But really the reality is that we don't know. Okay, now I want to talk about the probe last. And so there are obviously requirements for releasing the probe. And these requirements can be at odds with the UOI, which is the Uranus Orbit Insertion Maneuver. And there are two ways to do that. One is called deployment on hyperbolic, which is dropping the probe before UOI. And the pros are that obviously then you have less mass that you need to insert into a Uranus orbit. But the cons is that you can't really regulate the velocity of the probe. And you also have less, let's say, precision in targeting, where you want the probe to go inside of Uranus. The other way to do it is called deployment on elliptic post-capture, and it's dropping the probe after UOI. And the pros is that it reduces, well, the velocity of the probe is going to be reduced, and so also the mass of the thermal protection system. And the cons are obviously that you need a higher delta V because you're going to insert now orbiter and probe at the same time. And this is, I think, almost my last slide about probe science. And Dave didn't say 2 minutes, so I can take my time talking about this. So how much science can we get from the probe? Well, it depends on the instruments, of course, that it's going to carry. But also, an issue is the direct communication of the probe to the Earth, that it's really impractical. So most likely it's not going to happen. What it's going to happen is that the orbiter is going to be a relay for the data. And then this means that the orbiter has to point its high-gain antenna at the probe for as long as possible, because you want that gain, that high signal-to-noise ratio. And this could be at odds with other attitude requirements. For example, to do UOI itself, you might need to be in a completely different attitude. And then another question that people ask is how deep we can get with the probe. And so studies suggest that most likely we will have one atmospheric probe, and it will take measurements between 100 millibars and 20 bars. Is that enough? Maybe, but I'm sure that people want to go deeper if possible. It is possible. We could go deeper. We could go down to 1 kilobar pressures. But this means that, first of all, it's going to take longer for the probe to get to 1 kilobar. And this means that the spacecraft has to be pointed with this high-gain antenna there. And also, it's going to take a much more significant amount of resources, to make the experiment work, because now it's not going to go into 20 bars; it's going to be to 1,000 bars, right? And so it could be done, but then we don't have any resources left for other science, and it means that we go there and we drop the probe. And so, what is the balance, the right balance between orbiter science and probe science, right? My guess is that the answer to this question is somewhere in between. We do want to get both. We don't only want probe science. I'm actually, this is my last slide. This is takeaways and possible UOP timeline. So we've seen that there are many trade-offs and many compromises to be made when it comes to science payload, spacecraft, subsystems, probe science, and so on. And so, this is not going to be a one linear process. It's going to be iterative, and it's going to take some time. International collaborations should be leveraged to maximize the science return, and then, while maximizing the cost to each partner. And then we need, obviously, to get going on those trade-off studies, and I'm hoping that we will address some of these during this week. And then we need investment in research to better constrain the ring crossing hazard and also conditions in the upper atmosphere. Because it would be great to have a quantitative understanding of what are the risks implied in flying, between the rings and the upper atmosphere. So this is a possible UOP mission timeline, but don't come for me if this doesn't happen. So likely there will be a selection of a few scientists to provide initial guidance in 2025. Then we will have a new mission start in the late 2020s with a launch in the late 2030s and arrival at Uranus in the late 40s, around 2050, which is, if you remember, the equinox. And then with that, thank you. Oh.